Thank you. So it's great to be here. I'm Vahab Mirrokni from the the Google New York Algorithm Research Team. And I'm going to tell you about a couple of problems related to load balancing in cloud infrastructure. So this is where I'm coming from. We have a algorithm research group in the Google New York office, where we work on some market algorithms, on auction optimization projects, some large-scale graph mining projects, and some infrastructure and optimization projects. So I'm going to tell you a little bit about a couple of projects related to the third part, and it will be a brief talk, and more details are going to be available on our website. There are three stories that I wanted to cover. I guess I'll get to two of them in this half an hour. One is about consistent hashing for bounded loads, and then one is about overcommitment in cloud services. The third one is about an application of balanced partitioning in basically load balancing in the back end of search. So the first part of the talk, the first story is about consistent hashing with bounded load in dynamic environments. And this is a joint work with Mikkel Torob, who was visiting us for a couple of times, and then Morteza Azadi Muqaddam, who is a colleague. And we have a blog post about this, and the paper is also available on archive. The problem is about consistent hashing for dynamic environments. So let's say you want to hash the number of balls into a set of bins, and both balls and bins are very dynamic. They can be added or removed over time. And the main objectives in this allocation problem or hashing problem is that we want to come up with an allocation strategy, a hashing strategy that ends up in uniform bins. So we don't want to have some overloaded bins. At the same time, we want to be as consistent as possible and minimize movement of balls into different bins when we change the configuration. When we add a ball or remove a ball or add a bin or remove a bin, we want to minimize the number of changes in the system. So we want to be as consistent as possible. So that's basically the problem setting. So if I wanted to give you a wish list of properties for a hashing scheme, we want a hashing scheme to provide good uniformity across bins. We want to have more consistency for different reasons. One is the consistency is useful in dynamic environment. It's also useful it provides better caching properties. And then we want to have some and we want to be good against movements when we have dynamic environment. And we also want to have a memoryless allocation strategy, that when we want to compute the allocation again, if the configuration has changed, we don't need to have a lookup table to go and basically fetch where each ball is. We can just reconstruct the allocation from scratch. So the previous approaches that have been taken for this problem has been consistent hashing, or the core approach, where you hash balls and bins into a circle and you put each ball to the next bin on the circle. That's what people call consistent hashing, and that's useful and effective in dynamic environments actually, where we need consistency. And if we are thinking about basically an static environment, then the power of two choices can give us basically a good balance, uniformity among bins. When you are basically hashing n balls into m bins, you basically take two bins at random and you put the ball in the bin that has lower capacity or smaller number of balls in it. So if we want to tell you basically the properties of different type of hashing scheme, like consistent hashing and cuckoo hashing, or basically power of two choices based hashing. In terms of the maximum load, the consistent hashing can result in like log n like overloaded bins. Like if the average density of balls into bins is like density, the consistent hashing can result in like an approximation of log n. So one bin can be log n times worse than the average. But in terms of the average number of balls that we have to move, or the average relocation needed, it's like optimal. On the other hand, things like power of two choices achieve a good, like a much better maximum load. Like we go from log n to log n. But then we lose a little bit on the number of allocation, the number of movements or relocations, and like the maximum capacity is worse than a constant factor compared to the optimum possible. So what we wanted to achieve was basically to get to an approach that basically works against hard capacities. Even if I'm given like a hard capacity, if it's possible to achieve with a constant, with a static approach, I wanted to be able to achieve it. So what we can achieve is we can go for any epsilon to the optimum density times 1 plus epsilon, and the number of relocations that we need is of the order of like 1 over epsilon, like factor worse than the optimum possible. So if I want to tell you the algorithm in one slide, like the algorithm is very simple. It's similar to the linear probing algorithm, where we basically and consistent hashing algorithm, where we hash bins and balls into a circle, and then we declare the capacity of each bin to be 1 plus epsilon times the number of balls over number of bins. And then we implement this critical algorithm. So instead of allocating the ball to the next available bin on the circle, we first try that, but then if that bin is overloaded, we move the ball clockwise on the circle until we get to a bin that is like fine in terms of its capacity. So it's very simple to state. The problem with the algorithm is that it's not clear at all if it will be consistent. So is it going to be good against dynamic change in the system when we add or remove bins and balls? So what we could prove was that basically we know, first of all, that the algorithm by definition achieves 1 plus epsilon times the average load. What we can prove is that in general, for epsilon less than 1, we have 1 over epsilon square number of moves for each like necessary movement that we have to make. For larger epsilons, we have another bound that's much harder actually to prove. And we also observe like good properties of this algorithm, basically algorithm on simulated data. So I have to emphasize that the proofs for the, like bounding the number of movements is pretty technical. It's like tens of pages of concentration bounds and so on. But I'm not going to tell you about that. What I'm going to tell you is where it was used. And I have to emphasize that I did give a talk about this topic like a year ago in another workshop. But then I have some news about this and like some interesting story that I'm going to add to it. What was the question?
Why did you use two different hash functions for the balls and bins?
This is like a technicality that's not needed for the dynamic environment if we want to have good caching properties. Yeah, like I wanted to actually remove it from this part. Yeah. So So first of all, we deployed this for the Google basically pops up 2 project where it's like a scalable event streaming service, and it's like a service that basically is in charge of allocating clients to servers and can be deployed for any new basically like instance, and it's also like deployed as externally for cloud-based customers. And the interesting thing is that we face a variety of different type of scenarios in these type of problems, and some of them have this property that we are facing like a comparable number of clients and servers. And if you're familiar with consistent hashing, like this idea of consistent hashing with virtual beans fail like to solve this problem. But then the other interesting story was that we wrote this paper. We basically put it on archive, the theoretical result, which is like a, I don't know, 40-page write-up, and it's a completely theoretical write-up. Somebody, basically Andrew Rodland from Vimeo, managed to find this paper on archive because somebody else tweeted about it, and basically he was using some variant of virtual bean consistent hashing in like load balancing at Vimeo, which is basically the video serving system that we are familiar with. So what he did was basically to implement this like a strategy, and he also actually open sourced it through HA proxy, like load balancing open source system. But the interesting thing is that he also observed that it did improve Vimeo load balancing service and like a cache bandwidth usage by a factor of 8. And like in the blog post that he had, he posted this very nice like plot that shows like after he deploys this type of basically consistent hashing scheme, the number of cache misses drops significantly. So this was a great story for us. It was the first time that I basically, I don't know if it happened to you, that you write a theory paper, you put on archive, and somebody implements open source and use it for their own basically application without any interference. Later on, actually, he came to Google and gave a talk about his application, and the talk is also available online. So he would have given a much nicer talk about this and the story behind this. So I actually encourage you to look at this talk. I mean, it's like a practical talk, but then he mentions the problems with other type of hashing schemes, and we really enjoyed it, as you can imagine. So the first message of the presentation is this linear probing scheme with 1 plus epsilon extra multiplicative capacity per bin is an effective method to achieve uniformity, like good load balancing, good caching properties, and also good against movements, for number of movements in dynamic environments. That's about it for the first part of the talk. The second part is fortunately new, and I did not cover it in the talk I gave last year in a similar workshop at DIMACS. It's about overcommitment problem in cloud services, and basically it tries to solve a bin packing problem with chance constraint. The motivation here comes from basically load balancing setting on the cloud, where we have maybe even multi-dimensional packing constraints that we have to satisfy. But then basically there is generally like a very a good possibility that what we commit to is not going to be used effectively in the system. So you basically, you're running a cloud service, you may commit to run like some number of clients with maximum load of some number, but then the maximum load never materializes, but you want to also minimize the probability that you fail delivering all of these requests. So the idea there would be to overcommit a little bit, and basically, as a result, reduce the cost of buying the resources. significantly, but then at the same time, you want to make sure that you are taking a very, very small risk, let's say 0.0001% risk. So that's the motivation. What we do will basically formalize this problem as an optimization problem, like a beam packing problem with some constraint that we call chance constraints, and then we present a constant factor approximation, a non-line constant factor approximation for the problem, and then we validate our results on some real data sets. So I'm going to go over the problem of formulation and give you approximation factors. If I manage to get to some experimental validation, it would be good. So what is the model and the assumptions? So first of all, I'm simplifying the problem. In reality, the problem is not does not satisfy some of these assumptions, but they are not very significant. So first of all, I look at only the case that we have identical machines, so they have the same cost and the same capacity. We focus here on the single-dimensional problem, like the CPU is like the most important constraint that we have to satisfy, and we are assuming that we have a good estimate of the number of jobs and the processing time of jobs. So we are dealing with a stochastic problem for which we have some estimates. And then jobs arrive online and are independent over time. So under these constraints, we want to decide minimum number of machines that we can deploy and schedule these jobs, and maybe minimize the probability of not being able to satisfy all of them. So if I want to give you a problem formulation as a mathematical program, so it's a beam packing problem where I want to minimize the number of beans, and if the capacity of each bean is V, we want to make sure that on each bean we satisfy the capacity constraint. Each ball has to be allocated to at least a bean, and so on. So, but the processing time or the, let's say, CPU usage of the resource consumption of a job is a stochastic variable here, this AJ. So we basically substitute this constraint with what we call a chance constraint. We want to basically, instead of satisfying this constraint, we want to say the probability of satisfying the constraint should be at least like a probability alpha. So that's the first formulation that we look at. But then we substitute this probability also with with this form that we basically have a linear function, and also so we assume that we have, like, for the probability distribution, we have the mean of the distribution and some sort of a standard deviation. So this new constraint that I'm putting here does not model the whole problem basically faithfully, but the first part of the paper we show like 3 different scenarios that under which basically these constraints exactly model these other constraints, and then we observe that solving this problem itself, that now we call submodular beam packing, is a hard problem. So we first, for example, observe that this SMBP problem is the same as BP, the beam packing problem with chance constraint with under independent Gaussian jobs, and then we basically try to solve this new problem, and we observe that this is a special case of a submodular beam packing problem where basically the capacity constraint, basically the consumption or the usage of a set of jobs is a submodular function. So this function that I'm putting here is the sum of basically a linear function and a concave function, and if I define it in a set of jobs, it will be a submodular function. So we first, as I said, observed that this the submodular beam packing problem is equivalent or the same as the first problem I mentioned for general families of probability distributions. But then we observed that even this problem is not easy to solve. It's an NP-hard problem. You can do like a linear integer linear program, or so that's not tractable. Or if we model it as a general monotone submodular problem, we observed that for general monotone submodular functions, the beam packing problem that we were trying to solve is not actually solvable in polynomial time, even if we want to get a reasonable approximation. So getting better approximation factor better than n to the half, n to the power of half is not easy. That's like an information theoretic lower bound. So this story justifies looking basically at the special case of the submodular beam packing problem that we were looking at. So the challenge here is that we are solving a beam packing problem, but the capacity constraint, or the basically instead of defining a linear function over the set of jobs that we schedule, we have a linear function plus a concave function, which is the square root of another linear function. So the algorithm that we propose is what we call a family of lazy algorithms. We basically schedule jobs the best we can, and we open a new machine if we have to. So for example, the first fit algorithm or the best fit algorithm, or like these families of type of algorithm that only open a new machine when they have to satisfy this property. And what we can show is the lazy algorithm is actually a 8/3 approximation. So that's like the first theorem that we prove, and the proof of this theorem is not hard, but it's cute. It takes advantage of the shape of the basically function. We observe that for any infeasible set T that we have this property, we can prove like this. Basically, we can go to the linear version and show a gap, like a maximum gap of 4/3 between the linear case and the concave case. So that's a lemma that will be useful. And then we apply this inequality for any pair of machines. When we are like in the current solution, we know that like we only added machines when we had to. So basically, we apply this and then write the inequalities for all pairs of machines, and sum all of them. And what happens is that we lose another factor 2. So we go from 4/3 to 8/3. We also observe that in scenarios or in settings, and like we also characterize a class of problems that satisfy this property, that basically whenever we assign jobs to machines, we can satisfy this property that like whenever we open a new machine, we know that all the machines that are basically are already scheduled satisfy this type of inequality. We can get a 4/3 approximation. And for the first fit algorithm in particular, we can improve the approximation factor from 8/3 to 9/4. So these are for the online variants of the problem. Note that even for the offline variant of the problem, if I am given all the jobs, it's harder than beam packing problem, but still it's like a different and new version of beam packing problem with this linear plus square root function. So for the offline problem, we can give a basically 2 times up plus 11 type approximation, like a multiplicative factor of 2 and additive factor of 11. So that's pretty much what I wanted to tell you about the second problem. Maybe, yeah, like instead of giving you the summary for the, I see that they have, so like we have some simulations, like we take basically some real data sets we generate some instances from these data sets, basically based on like the same type of distribution. So what we do, basically, we take the real instances, we generate parameters of the real instances, and then we generate instances based on that, so that it's repeated. You can repeat the simulation study, and then we observe that our algorithms perform well on those instances, and we get, in some cases, 8 to 14% like cost saving. And yeah, so that's the summary of this part. We talked about the beam packing problem with chance constraint and a variant of the submodular beam packing problem. We observed that lazy algorithms are 8/3 approximation, first fit is 9/4, and the offline algorithm is a 2 approximation. And there are some insights that we can get out of these algorithms. So this is the related work. So I thought that I can get to defining the third problem, or I should wrap up.
I think for 6-7 minutes.
Okay, so 5-6-7 minutes is fine. Like, I guess this is also a cute idea that I wanted to deliver to this audience, and it's very related to data center. The third topic is, or story is about application of balanced partitioning to web search. So what I mean by balanced graph partitioning. So and this part is like a real engineering effort with engineers in the back end of search at Google. So what we do is, first of all, what I call balanced graph partitioning problem is where I am given a graph, and I have node weights and edge costs, and I want to divide the graph into almost equal pieces, like K clusters that basically are almost balanced in terms of the weights of the vertices. So this is like a very hard problem. It's balanced partitioning with like minimizing the cut. So one thing that we have is we have a tool that solves this problem for pretty large graphs empirically, or like we have an applied distributed algorithm that does this, and this is an application of this problem. So the observation that we had in the back end of web search is that caching is very important, and we want to basically, when we satisfy queries like in the server, the backend server, it's important to try to be consistent in allocating queries, and more than that, it's good to be consistent in terms of affinity of the queries that are allocated to the same server.
Question?
Yes.
Why do you want your queries to be uniform? I'd have thought non-uniform would be better for caching. I mean, if you're always asking the same query, that's the ideal for caching, right? So in what sense is uniform? So the
uniformity is needed because of the capacity, like the capacity constraint on the servers. The uniformity is important because you have to basically deal with you have some metadata to handle that if you want to handle that query. But the caching property is the only thing that's important is that we want similar queries to end up in the same server. So basically, yeah, let's say we have, when a query arrives, we have a route. It basically allocates it to different replicas or different servers. So the question that we wanted to answer is basically for each of these allocation problems, which replica we want to allocate this to, and this is for each query we have to make a decision. Basically, the way that it used to happen was basically doing more uniformly to make sure that we can satisfy the resource constraint on the servers. But the design that we came up with was basically, let's say, this is an example. We come up with basically a set of similarity between terms that have to be handled. Basically, we do a clustering algorithm, and we try to cluster terms that like tend to happen together in the same cluster, and when a query arrives and it's clustered in one of these, like let's say here in like 3 clusters, we make sure that all the queries that are clustered are always allocated to the same replica. So this way, we make sure that similar queries end up in the same replica, and they have much better caching property. Yeah, so like offline, what we do is we look at logs and like the relation between terms. We build like a term query graph, or like a query to query graph, and then we do balance partitioning of that graph using the technique, the tool I mentioned. And then online we allocate queries based on this offline allocation or clustering that we computed.
Vahab?
Yes.
How do you assign? You need to have the weights, the costs.
So good, like here what I'm telling you, like because we have like many terms to handle, we could have also make it weighted and like be balanced in terms of the total load of these terms or something, but for now at least we didn't need to take that into account because we have like too many terms. Like I'm talking about all terms, for example, in web search, or not all terms, like all the head terms that are like frequent enough for which it's worth like doing something like this. So I'm talking about like, let's say, tens of millions or whatever number of terms here. And we ignore the weight of the terms for this. So what happens is now we want to basically, so like here I'm trying to justify the exact objective function that we try to optimize, which is we want to make sure that when 2 queries appear in the same, two terms appear in the same query, like we want them to go always to the same server. So like I can formalize that as like the cut size in this graph that I can build over queries. Yes, so yeah, like I think I have actually a slightly different version of the slides here, but okay. So yeah, like I wanted to maybe tell you about the balance partitioning algorithm that we applied, and we do have it here. Like basically, in order to solve this hard problem, what we do, I mean, it's a hard problem. You can't get a constant factor approximation. You should do a semi-definite program or whatever if you want to get a square root of log n approximation. But we can solve the problem on graphs with like billions of edges. So what we do is actually we take the graph. The first thing we do is we do like a hierarchical clustering of all nodes of the graph, basically with the technique that we call affinity clustering, and we can prove good properties of this algorithm. But like for the purpose of balance partitioning, the way we use the hierarchical clustering is we use it to order the nodes. Like we look at the order of leaves of this graph, and then we apply a 3-stage algorithm that takes this order and try to reshuffle to minimize the cut. And this is very effective and can be done in like MapReduce framework. For the initial embedding, if we have a geometry graph, we can use again the space filling curves. But then for general graphs, we use affinity clustering to find the order of leaves. Yeah, so and this slide describes the affinity clustering. Like the algorithm, actually the hierarchical clustering algorithm is pretty simple. At each step, we try to allocate each node to the closest node in terms of its like similarity. So, and the weight of the edge is something like the number of common neighbors of the nodes that we consider. So yeah, we look at different data sets and we have good results there. So yeah, like I think you can look at the balance partitioning part. like on our website. What happened was that when we applied this to the back end of search, we did get like a big improvement in terms of the number of cache misses for that problem, like 25%, and that was a big win. And this is take home point 3. That's basically these like building these graphs over queries and using them in the back end of like a search system or like a serving system like that can be useful for better caching property. That's about it. Thank you.
So let's have one question before we move on to the next speaker. Okay.
Okay, thank you.
Let's make the speaker again.